Hello everyone. Welcome to our low temperature thermochronology online lectures. Today, we'll be continuing with studying Chapter 5, Fission track thermochronology theory background. After learning the first three sections, today we'll be continuing on to fission track annealing. Fission tracks are malleable features which will fade with increasing temperature. This phenomenon is called fission track annealing and represents the major strength of this method. For example, for minerals analyzed from a drill hole with a downward increase in temperature, fission track length will shorten and the number of tracks will decrease with increasing depth in the hole. Consequently, fewer tracks will be contained and the age estimate becomes younger in deeper samples. In this case of apatite, a zero age is eventually reached at a depth of about 3 to 5 kilometers. Fission tracks shorten or anneal when the host mineral is at an elevated temperature, as a consequence of a thermally activated diffusion process. For instance, when temperature is higher than closure temperature, damages or fission tracks are annealed and the lattice is repaired. When environmental temperature is lower than closure temperature, fission tracks are stable and will be accumulated in time. The temperature range over which annealing occurs varies for different minerals and also depends on the cooling or heating rate. The concept of a closure temperature for the fission track system, for instance, the temperature of the system at the time given by its apparent age, is generally an oversimplification. For example, 110 plus minus 10 degrees centigrade is commonly adopted for the normal closure temperature of apatite fission track system. Yet, geological examples indicate that significant annealing occurs over a temperature range of at least 60 degrees centigrade. About 220 degrees centigrade is proposed for a highly radiation-damaged zircon, and the closure temperature of above 300 degrees centigrade for zircon with low to zero radiation damage. And this range is generally referred to as the partial annealing zone, or PAZ for short. The 60 plus minus 10 range for apatite is a minimal range. The partial annealing zone, proposed in 1979 as the partial stability zone, is a temperature range located above the total annealing zone where there is no track retention, and below the total retention zone where there is negligible annealing occur and fission tracks are stable. The temperature range of apatite partial annealing zone ranges from 60 degrees centigrade to 120 degrees centigrade, as determined from several natural examples and laboratory experiments. It is well known that the mean of a distribution of Indus tracks in apatite is 1 to 1.5 micrometers longer than spontaneous tracks measured from samples that are considered to have been at near surface temperatures since their formation. This suggests that annealing occurs at a near surface temperature over geological timescales. Annealing experiments, as well as application of the models to geological timescales, give a temperature range of 230 to 330 degrees centigrade to the zircon partial annealing zone, with a range of 240 plus minus 30 degrees centigrade applicable for most natural zircon. This figure here shows the proposed temperature range of partial annealing zone of zircon. Here shows examples of characteristic cooling paths. In the case of extremely fast cooling, the resultant fission track age represents formation age. When the cooling is a relatively fast cooling, it is considered that the fission track age is real cooling age. And when the cooling is relatively slow, we consider the fission track age as apparent age. In the case of reheating, fission track age is also an apparent age. Grains recording heating and cooling event by track length shortening and growth, generating responses in fission track ages. Then, distinguishing and comparing the characters of different confined track length distribution will illustrate related thermal history scenarios of the host rock experienced. Now, let's look at the track length distribution, which is characteristic for the type of cooling. For rapid cooling, as is shown in this figure, the track length distribution is a tight one. And in the case of a relatively slow cooling, we see tailing peak distribution of track length. In the case of reheating, a very characteristic bimodal distribution of track length is observed. For some different types of cooling, we may be facing the same fission track data, however. For example, here, we have 3 scenarios of cooling, and in all these 3 scenarios, we have relatively slow cooling, relatively rapid cooling, and a reheating scenario. And corresponding to these different scenarios, we have different length distributions. However, under all these different scenarios, we could have the same fission track age. In this example here, all the 3 scenarios will give us the same 60 million years. Factors controlling annealing including time and chemistry. Single grain fission track ages in a sample from present-day temperatures of 95 degrees centigrade show a clear and constant variation with chlorine content. Chlorine content exerts a significant control on fission track annealing rate in apatite, as also seen in laboratory experiments. It is shown that chlorine-rich apatite is more resistant to annealing and sustains higher closure temperatures. Chlorine content is therefore measured in every grain in which either age or length data is collected. The parameter dpar is defined as the mean maxima h-pit diameter parallel to the c-axis. For example, here, the figures show that dpar measurement shows clear correlation with the chlorine content and with FTH, which indicating that dpar is an important chemistry parameter for fission track dating. The complete fission track analysis should therefore include, first, fission track age, second, track length measurement, which means confined track length measurement, and chemistry parameters, normally the chlorine content and dpar, and if possible, modeling of the cooling path. Thank you very much, and the above is all for this section.